Is that what it is? Wow. My writing is such chicken scratch. Oh well. Okay. So, Professor Nick Najad's out of town, as you know, and he asked me to do a guest lecture basically on my master's and part of my PhD research, which is on ultra low power radios, particularly for sensor networks. So this has got some relevance partly to people who are doing the project, in that at least you'll see one way of making things low power. Also, it's just a chance to see all these different techniques and blocks we've used and that you'll see for the rest of the class, all in one place, sort of integrated together. So how you might actually design a whole radio based on some of the techniques we've looked at, and also on some techniques we haven't looked at. So I've got it in PowerPoint because it's hard to do this many schematics by hand, and there's measured results and things. But PowerPoint is, as you probably know, is not really the greatest interactive lecture mechanism. So if anything's confusing, grab the mic and yell, and I'll draw stuff because I don't have enough slides to go for 90 minutes anyway. And there are several tricks in here that aren't things you've seen before, so it's probably worth taking the time. And also, I'm writing the next homework, and this is the material, so it's good to pay attention and not fall asleep, since you might see some of it again.
Oh, wow.
Oh, yes. Homework, because of the midterm on Thursday, homework and NSFs, homework will be due next Tuesday. This homework that's due right now. But we will assign another one on Thursday that's due on the next Thursday. So it's not any less work. It's just if you have a really bad schedule, you can shift this work till the weekend. But if you don't, I suggest doing it now. Anything else? Any other questions before we start? All right, so to the computer.
Are you dual displaying?
What do you mean? Oh, I'm not. That's the problem. Thanks. I was wondering. How about now? All right, there we go. Okay, great. So low power radio circuits. And I'll define what I mean by low power. So the basic idea, I was working with Chris Peaster, who's a professor here, as many of you know, working on smart dust. And the basic goal of smart dust is to make a single chip with as few off-chip components as possible that'll sense information, process it some, store it, and then communicate it, usually through several jumps home. So this one good way of implementing that communications with radios. So that's what I was working on. Okay, so what are our high-level constraints? The biggest high-level constraint is cost. We're trying to make these so cheap that you can basically buy them, distribute them, and just not worry about them until they die. And that means something like on the order of $1 or less. So what does that mean? That means one cheap chip, and particularly in this case in something like 0.25 microns CMOS, so that's pretty standard. In fact, it's kind of obsolete now. And as few off-chip components as possible. So you need to have a battery. The highest density batteries you can buy are lithium coin cells, at least in terms of small ones. So that's a 3-volt battery. A crystal, so you can synchronize your network. You use quartz crystals because their frequency of resonance is very, very tightly fixed. It doesn't vary very much with temperature and things. So if every node has a crystal on it, then they're all on the same clock. And they only have to sort of talk to each other occasionally to keep synchronized. You need an antenna so you can radiate your signal. And then the only other thing we let the radio have was a single off-chip inductor. And the main reason for that is that the process we were in was not good for high Q inductors. In fact, it wasn't good for inductors at all. Oh, okay. Yes.
Why do you call it smart dust?
Really,
It's not dust.
no, it's more like gravel. Smart gravel is probably a more accurate description for what I was working on. It would still hurt if it hit you, yeah. Okay, so those were our basic constraints. From a performance point of view, we were shooting for about 10 meters of range. That's just basically 2 rooms in a largish building like this. Data rates in the order of 100 kilobits per second. We would take 10 kilobits per second, but not megabits. A really low duty cycle. So the idea of these things is they spend most of their time off with basically a clock running and nothing else. And then every once in a while, when the clock times out, they wake up, they sort of listen if there's anything they want to hear, they take some data, they send the data home, and they turn off again. So a low duty cycle, but a really long battery life. So something like 5 years. So you distribute them and you leave them until they're obsolete. If you take those different numbers and combine them, you end up needing a power consumption when the radio's on of about 1 milliwatt. That's basically just the cheapest battery you can get, divided by 5 years with a 1% duty cycle, and that gives you approximately 1 milliwatt. So there's a few ways few techniques I'll be hitting as I go through this on getting down to 1 milliwatt. One technique is to stack circuits so that your bias current gets reused over and over again. And the other trick is to use my one very high Q inductor to tune out as many capacitances as possible, so that I basically get a power reduction by a factor of Q. Okay, so here's the top level of the chip. Just point out the critical components. At the core of it is an oscillator. You need to be able to generate RF signals. We haven't done this in class yet, but I'll go over one oscillator architecture today, and that's at least a sort of a forward view of what oscillators are like. You need some sort of frequency centering algorithm. Usually this is a PLL, but PLLs are actually not so easy to implement digitally, and we wanted to make as much of this as digital as possible, so I'm using a slightly different algorithm. We have a transmitter, which basically just buffers the oscillator signal to the antenna. So the way you send signals is you modulate the frequency of the oscillator. That's a frequency modulation. And then the transmitter just buffers that out. Other techniques are possible. You could potentially modulate the power of that amplifier and then get AM modulation, for example. But FM tends to be or FSK as it's called, frequency shift keyed modulation is the sort of simplest to implement. And finally, we have a receiver to receive FSK signals and down-convert them and demodulate them to bits. So the overall goal here is to have only these off-chip components I've outlined, plus a battery, these 3 off-chips, and only talk to it in digital, sort of low-frequency digital. So just put in transmit bits. I lost myself. Put in transmit bits, get out receive bits, nothing else. So that was kind of our high-level goal. One other thing that I won't get into too much, but we developed some techniques on, is how to stack things well. So how to set up biases so that you can reuse the current in different ways and still have everything operate fairly independently. Okay, so I'll start with the oscillator. We use a negative resistance oscillator, so we'll go about this a little bit more, but that's the negative resistance. It's basically 2 CMOS inverters cross-coupled. And the way you think about this is basically 2 GM stages cross-coupled. And you can sort of imagine, if you look on this, if I increase the voltage here relative to here, these are typical sort of negative GM, so this will pull current in. So if the voltage goes up, and let me just sort of, I'll wave my hands. You do this with the voltage. If you do this with the voltage, this will actually suck more current from this side. So it'll actually pull current the opposite direction from a normal mixer, from a normal resistor. And so it acts essentially like a negative resistance. And so the key is, if the negative resistance is stronger than any real resistance there, then you're unstable, and you will automatically try to lock up. Now, if you put a high Q LC tank across this, the place where this is highest resistance, where it's least strongly resists the negative resistor, is at its resonant frequency. So it'll be unstable at the resonant frequency, and it'll oscillate. And so now you've got an oscillation that's set by the LC coefficients of your tank here. This is basically the most common type of RF oscillator out there. So that's great. Now how do you control the frequency of oscillation? You typically vary. My mouse there. You vary this capacitor. And in this case, our requirements were, we wanted to cover the US ISM band, which is just a band from 902 to 928 megahertz. But we wanted to cover it in spite of variations in process, so capacitors and transistors vary, and also variations in our off-chip inductor. The nice thing about this is, remember that resonant frequency goes as the 1 over the square root of LC. So if your capacitor varies by 10%, your frequency is only varying by 5%. You get a little bit of help. So anyway, that's where these numbers roughly came from. We estimated about 10% realistic variation in our capacitors and a 5% variation in our inductors. So hence we need a sort of a 7.5% plus or minus coverage. The inductors we have available that were relatively cheap have inductances on the order of 17 nanohenries and with a Q of about 30. So that's actually a pretty good inductor. You really can't do that on chip even now. You're going for about a 1 volt swing. You need 1 volt so you can really turn transistors on and off, and I'll get into why that's important later. And then we just try to make the bias current as low as possible. And if you take the inductance in the Q and the swing, you end up needing a bias of between 2 and 300 microamps. This is also aligns nicely with our 1 microwatt goal because we have 3 volts of supply. So 300 microamps out of 3 volts is a microwatt. So one way you could say is that this oscillator is taking all of our current. We're already done. But the thing to notice is that the oscillator only needs about 1 volt of headroom. So you can actually reuse that current with the remaining 2 volts to do other things. So we'll get to that in a minute. Okay. So just some simulations of that thing I showed you, just so you know what an oscillator simulation looks like. This is a typical transient simulation. You can see it ringing up, and then it saturates once it's reached its maximum oscillation amplitude. This is just a spectrum from over here. Phase noise isn't something we've talked about yet, but this describes how spectrally clean the oscillation is. Basically, the farther out you go in frequency, the less, a better way of describing it. Basically, if phase noise were infinitely low, then that would mean you were only oscillating at one frequency and there's no variation. But realistically, any sort of noise that gets into the system will tend to jiggle the oscillator, and the phase noise is a measure of how much it's being jiggled. I think we'll actually probably spend a fair amount of time on that in a few lectures.
Exact.
Oh, time. This is in nanoseconds. This last one is just to show that one of the bias points inside of the oscillator actually varies as it rings up, which has some interesting properties in terms of stability, but I'm not going to go into that.
Won't the oscillator have a square wave? So, I mean, oscillator output is square, right? So you'd have F3, F5, F. And wouldn't you see that in your phase noise plot, or is the x-axis for those two not the same?
For here and here, they're very different. So this is a relative frequency coming off of the oscillator, and this is just the raw spectrum. So that's gigahertz, and this is a logarithmic plot out to like 100 megahertz.
No, but if you didn't plot that out, you would see the FTF.
Yeah, there's definitely spectral energy there, yeah. Okay, other questions? I'll move on. Okay, so how do we do that variable capacitor? So I just drew it like this, but that's not very helpful. So one way to go about this in a more pure analog system is you put in what's called a varactor, which is often just a reverse bias diode, and you change the bias, and that changes the capacitance, and there you are. But that requires a nice, clean analog signal, and I'm trying to make this, and a clean analog signal normally means big capacitors, and that's off chip, no good. So I was trying to do it all digitally. So I used one of several different kinds of switchable capacitors. In this case, I used what I'm calling an inversion cap, which basically just makes use of the fact that if you take a typical FET and you switch it between strong inversion and strong depletion, so not avoiding accumulation mode, then the capacitance changes dramatically, because in depletion mode, the gate capacitance is basically either to the source and drain or all the way down to some really deep depletion region. Can we switch to the so if you let me just draw it. So you have typical NFET, or typical FET, kind of scaled funnily. If you were to look into the sort of the state of the semiconductor around this, you'd see that there's a depletion region here, also around these are PN junctions, right? But also across the middle here. And depending on your gate voltage, the depth of this depletion varies. Now, one thing you almost never see in sort of simple stuff is that at some point this goes into accumulation mode. If you bias it one way enough, this depletion region goes away, and that's accumulation mode. But that actually depends on the gate to bulk voltage. So what you can do is you can actually make the gate to bulk voltage huge, so you always have a depletion region, and then turn the FET on or off depending on the drain and source voltages. So that the drain and source actually are what give you a channel or not. So deep depletion is just a very large gate bulk voltage. So you have a very large depletion region. It makes a very small capacitance. So it basically means that the capacitance that dominates is now the overlap cap here, rather than something else. And then when you switch modes into inversion, then suddenly you have this nice strong capacitance due to the channel, and it's relatively high Q because the current can flow out both sides. There's a bunch of math you can do, but it turns out to be a very high Q capacitor when it's on. But it's very digital. So if you these are in simulations, but if you plot the capacitance as a function of essentially VGS, you can see is that there we are. The blue one is an AC simulation, so it's just the small signal capacitance, and you can see it changes very rapidly. It's a very sharp turnover. The second simulation is actually for a large oscillation signal, and see it's a little bit smoother because essentially as you oscillate, you pass back and forth between a lot of capacitance and no capacitance. You looked like you had a question. Okay. Now, one thing to notice is that the capacitance changes quickly, but what really changes as you switch the bias is Q, because as you increase the bias, the channel gets thicker, and so the resistance drops. So you really want to switch it digitally from all the way off to as far on as you can get it without blowing it up. So the operation region is actually either this corner or way up here. The other way to use a FET as a variable capacitor is in accumulation mode, which you can more easily do with PFETs usually. And then you get this sort of smoother curve. So the way I implemented this is I actually made it a binary array. So I had a whole bunch of these inversion caps lined up, scaled in a typical factor of 2 or power of 2 way, and then just digitally turned them on and off to hit any number in between. One problem is I needed a huge range with high accuracy, so you couldn't actually get a single 12 or 16-bit array that would match perfectly all the way through. So a pretty good way of getting around that is you break it up into sub-chunks that are each, say, 4-bit chunks. Each of them are internally matched. And then, so for example, you have one chunk that's a picofarad, 2 picofarads. Each of the bits are 4 picofarads, 16 picofarads, or 8 picofarads. That's your matched binary array. And then you have a smaller array that you could have made, half a picofarad, quarter picofarad. But instead of that, you make it 0.6 picofarads, 0.3 picofarads. So there's a little bit of overlap. What it means is that when you as you count your number up, your capacitance rises and then has these little sawtooth moments. But it means that you can hit every frequency, and just some frequencies you can hit more than one way. And so in the end, you have to put in some sort of extra coding to sort of eliminate the overlap zones. But it means that you're sort of not too dependent on matching, because if your matching is a little bit off, you can still hit every frequency. You just need a slightly different calibration code to do it. Mike?
Why didn't you use a variable MEMS capacitor?
Because I'm operating in a normal, sort of standard process, and a variable MEMS capacitor would cost me more than I'll ever make in my entire life.
But what's the advantage of, like, say, using the MEMS capacitor versus using, if you can make a variable capacitor using state-of-the-art CMOS technology, analog circuit, why is it interesting making MEMS capacitor?
That's a good question. There's some answers to that. One is that this is a digital method. So there are some situations where you can't do it. You really can't do it digitally. You really have to have a single analog signal driving your variable capacitance. In that case, you're working with a more traditional varactor, and they're typically pretty nonlinear. So you might be able to get better linearity with a MEMS cap. The other thing you might be able to get is better Q. So the switchable caps, you can usually get pretty good Qs of sort of 40 plus. But a varactor, and the varactors are sort of the same range. So if you can beat that, if you can beat 40 for your Q, then it makes sense to use something like a MEMS cap. But I don't think it's absolutely clear that you need them. I think it's that's an area of research, if you can make them good enough to be worth it. Okay.
With all that mess, how can you get the Q of 30 that you were before?
Okay, well, the trick is that every one of those capacitors, basically the Q of the whole array is the same as the Q of any one of those capacitors, because each of them has the same ratio of C to R. Does that make sense? So if you put them in parallel, your C goes up and your R goes down proportionally, and your Q stays constant. So there's really not much mess. It's just a big parallel cap with some high Q. And the trick is to bias it appropriately so that the Q is high. That's kind of the trick. My estimates on this was actually from simulations, which aren't great, but okay, are a Q of approximately 100. Really, really good. But I kind of think that the model wasn't really set up for this. I had to simulate some other things and then back out numbers to estimate Q, and I don't know that the model was that accurate. but it's good enough that it actually worked. So that tells you it wasn't too bad. So then the only problem is that your LSB, the smallest thing you can get, is the smallest transistor you can get, and that's maybe not a small enough capacitive step. So to sort of tack on a few more bits worth of accuracy, I used a single 4-bit DAC driving a single true varactor that's just variable, and that picked up my last few, like literally attofarads of capacitance variation, like tens of attofarads. That's tiny, really hard. Anyway, so this just gives you an idea of what I was saying. The varactor is actually, it's not very linear, so it has a range of about a factor of 10. Its biggest step, its full range gave me about 100 kilohertz, which is more than the LSB of the next array up. So I know I have overlap. I can cover variation. Sorry. So the columns are, the minimum step is my LSB, and the range is essentially if I switch that array from all the way off to all the way on.
So what's a varactor?
Varactor is a variable capacitor. So in this case, the varactor was an accumulation mode PFET. It's just a variable capacitor. Okay, so that's just the basic idea. Is rather than doing a traditional analog control, I do a really heavily switched control. If you look at most modern oscillators, there's some hybrid of the two. There's usually some sort of fine analog control and then a coarse digital control. And then this was just an extreme version where I essentially made it so digital that the analog went away. Okay, so just some measurement results so you believe it works. This is the measured frequency across just the MSB settings from the lowest to the highest, and you can see it covers about 140. What did I claim? Yeah, about 140 megahertz of range, around 900 megahertz. So it hit my band of interest. It's a little low. That always happens. And it hit my range I wanted. The LSB precision was in the range I wanted, about 2.6 kilohertz. So my sort of design spec was an FSK signal so the way FSK works is a 1 is coded as one frequency and a 0 is another, and you just switch back and forth. And the separation of those two frequencies in this design was about 100 kilohertz. So if I have an accuracy of 2.6 kilohertz, that means I'm much more accurate than I actually need to be to send those 2 bits and to distinguish them later. So that was my spec, and I met it. Phase noise is way worse than I modeled. We haven't talked about it yet, but let this be a lesson. You can do great phase noise simulations and not remember to include bias and be completely messed up later. So bias got me. And I was able to help it some in a second round of design, but it was the limit on the design in the end. And then there's one other effect that we may or may not get into called squagging, that is a way that sometimes oscillators fail. Rather than just usually sort of simple oscillators when you're not really pushing on power, either they work or they don't. If you give it too little power, they just turn off and they don't oscillate. And you get above some critical bias current or bias power and they turn on. But sometimes instead of just turning off, they sort of turn off and then wake up and then turn off and wake up and turn off and wake up and turn off, just sort of, and give you this awful AM modulated disaster. And that's what this oscillator does if you give it too little power. So it's very easy to detect when it happens. You can put just a little peak detector on there and you know what's going on. So it's easy to avoid, but it's just kind of an interesting aspect of the oscillator. This one doesn't just die. It kind of screams a lot first. Okay, so those are the basic oscillator results. So now back to the top level. So we've talked about the oscillator. Now I'm going to talk about a little bit about frequency centering. Okay, that's this part. And the basic idea here, this is not actually the best way to do it, but for low power, it works pretty well. The idea is the oscillator is running all the time, and you just count cycles. And every once in a while, you latch in your present count. And you latch in the present count based on your crystal. So every time the crystal goes through one cycle, you latch in a new count number. And if you subtract the two successive counts, that tells me how many cycles your oscillator went per crystal cycle. And that basically gives you a ratio. So you get a ratio of frequencies. And that's if you know the crystal frequency very accurately, which you do, then you now know the frequency of your oscillator as well. So then you just put that into a feedback loop. You put an accumulator in there, which is basically an integrator, and you compare it to your wanted frequency, your wanted ratio, and then feed that back. Now, when you design this, most of this is just low frequency digital. It's all running at the frequency of the reference, which is, in this case, was 32 kilohertz, I think. So really low frequency. There's no power there at all. But the one place where there's power is in this initial divide down. When you're counting cycles of the oscillator, you're counting a gigahertz signal. That requires fast digital. So I spent some time doing some custom digital design to try to cut that power down. And particularly in the very first count, I actually put in a specialized divide by 8, which just takes the frequency down by a factor of 8 before you start counting accurately. And I'll show you how I implemented to make that very low power. So here's our oscillator again. I've stretched it out a bit. And I feed it into, this is my divider. And it's, I always called this a ring divider until last year's ISSCC when someone else put it up there and called it a Johnson counter. So now I know it has a name. Before that, I never knew. So the basic way this works, I'll show some simulations in a moment, but is that every cycle of the oscillator, one of these D flip-flops takes its input and transfers it to its output. So you can imagine if, say, we started with this input at 1 and everything else 0. Then after one cycle, that 1 propagates to here, and then to here, and then to here. And after the fourth cycle, it's to there, and that comes through the inverter and makes this a 0. Now the 0 propagates through. And so a total cycle takes two propagations through this loop, or 8 cycles, and so it divides by 8. And then the more typical divider looks more like this. These are actually T flip-flops, which is a D flip-flop with an inverter around it. And these each divide by 2. So now you take the signal into here. Every time this clocks, this output changes state, 1, 0, 1, 0. And so each of these successfully divides by 2. Now, it's a little funny. Why did I bother with this weird divide by 8 thing when I could have just gone straight into one of these and immediately started dropping my frequency? And the benefit is only clear once you actually look at, so that's my signal flow. If you actually look at the guts of one of these guys. Basically, this D flip-flop is just 2 inverters with 2 switches. So each time one of these switches opens, an edge propagates to the next inverter. Now the reason this is low power is that the switches are effectively differential, and they're being driven by my oscillator. And my oscillator is high Q. So all the capacitance associated with the switches is being tuned out by the inductor. And so I get an effective power reduction of Q. It's not quite that good, but it's very close to. And so then the only power I'm consuming is to switch 2 inverters per cycle of my oscillator. And only one of those is switching high. So in effect, you're only consuming 1 inverter worth of switching power per cycle of my oscillator. Okay, so these 2 lines here are connected to these 2 lines here. So this looks like a capacitor, and there's an inductor across it. And so it resonates. So what that means is, if it's pure digital, every time you charge up a capacitor, that's dissipative, right? You're charging it through a resistor, in effect. Now when I'm charging it with an inductor. So a lot of that, when the charge comes off here, a lot of it, instead of being dissipated, it actually flows back through the inductor. And so I get a step up of Q. Does that make sense? So basically, this power savings is coming because I can drive my switches differentially straight off my inductor, and so get a big reduction in input drive power, and then only consume power in my inverters. And I did an analysis on trade-off between how many stages I have, there we are, stages in here, and how many stages I then needed in my successive divisions. And 8 turned out to be about the right point where you get the least overall power consumption.
What do you trade off? I mean, why not go above 8? So
to more 8? Well, the problem is that the more of these you have, the more load you put on the oscillator, because it's more capacitance. And at some point, that power consumption starts dominating over the power saved in your other divider. Okay, so just a simulation to show how this works. This was the first look at the first flip-flop. This is the original signal coming in. 1 full cycle later, it gets transferred to the second one, to the third one, to the fourth one, gets inverted, and then continues to propagate through the chain. So it's just the single lower frequency signal running around the circle. And when the thing fails, just so you know, when you give it too little bias current, then it starts skipping cycles and dividing by other numbers like 9. It'll essentially miss a whole cycle here, and one of these will be longer. It's actually turned out to be pretty hard to test in any way besides just functionality, but it works. I fired the thing up, and the frequency always went where I wanted it to. And we could show it failing if we cut down the bias current to the divider enough. It would suddenly start miscounting, and the frequency would go all wrong. That's all that shows. Okay, so back to the top level. So next, we'll talk about the antenna driver, the transmitter. Basically, the goal of the transmitter is just to buffer whatever the oscillator is doing. So the oscillator is some frequency modulated signal, and it just gets sent to the antenna. You might ask, why not just hang the antenna straight off the oscillator? I mean, that's even more straightforward. And the problem is the antenna looks comparatively low impedance relative to the core of the oscillator. So that resonant oscillator, when it's on frequency, has an impedance of about 3 to 5 kilo ohms, and the antenna has a resistance of like 200 ohms at best. And so now you've essentially DQ'd your oscillator by a factor of 20 or more, factor of 10, and so you have to consume 10 times as much power in the oscillator, and that's just not at all worth it. So instead of that, we need a buffer. Now the problem here is, let's get down to it, we can't do very much impedance matching. So the way you typically make a transmitter efficient is you just match the impedance to the antenna so that you can, every bit of power that comes out of your amplifier goes straight into the antenna. But if we're going to be cheap, we can't have much in the way of off-chip inductors, and the process isn't giving us on-chip inductors. So we need some other way of doing good matching. And the problem here now is that we have a 3-volt power supply, but our signal swing for the sort of powers we're interested in is only about 200 millivolts. So we're barely using our headroom at all. It's completely inefficient. And furthermore, we need a lot of current to do it, to match our impedance. So it's just not a good matchup at all. So how do we get around that? First thing we do is we stack with our oscillator. So I said before the oscillator needs about 300 microamps, but it only consumes about 1 volt out of our 3-volt supply. So we just we take the oscillator, we take all the current from the oscillator and use that in our output driver. So this is just sort of a stack up. Here's our supply at, actually I think I did these simulations for 2.7 volts. So here's the oscillator operating on its, off of its 2.7 volt supply, and here's this bottom voltage here. This is a little better. Now our voltage left over is more like sort of 1.82 volts to 1.6 volts. Still not a very good match, because if you say 300 microamps out of 1.6 volts, that's equivalent to about a 2.4 k ohm resistance. Just do the raw sort of bias numbers. And we're targeting more like 200 ohms, so no good. We can make it a little better by doing a push-pull amplifier. And what that means is that there's these 2 transistors running, driven with opposite phases, and only one of them is on at a time. So either this one is on in essentially a common source configuration, or this one is on in a source follower configuration. And as long as only one is on at a time, the other one's completely off, then essentially we're driving twice as much current as the bias current. Half the time, all the current's going this way, so it's not just the bias current, but all the extra stored up charge. So 2 times bias current, and then this guy turns off, this turns on, and it comes back the same doubled amount. So that gives us a better impedance match. Now it's more like 1.2 k ohms, still a terrible match. So then we stack up 2 of them, and we bias them such that the current flows this way, but now we combine the output signals. What that means is that, and I have a great animation for this. So first of all, just to get a feel for what we're talking about, by stacking it up, we've now we replicate the signal twice in our bias stack, but now it's on top of each other, so we pretty much use up all of our headroom just replicating the signal over and over again. If you wanted to follow a little bit of charge through this, first we'd go into the oscillator and oscillate a bit. I made this for my quals, and Chris Peter he's just dying when he saw this. He thought it was so funny. Then you send the electron to the antenna, you store it, you send it to the antenna again, you store it, and then finally you dissipate it. So you basically make as much use out of your little bits of charge as you can. You want to see that again? Yeah, okay. Woohoo! Oscillate, baby! No, I'm sorry. So we've allowed ourselves 1 extra inductor here on the antenna, and the idea is it's series with the antenna. So in principle, you could actually build it into the antenna. If you're having a wire as your antenna, you just make the wire longer and coil it up, and you've got an inductor. And actually, most of the testing we did, we had an explicit inductor in there. So instead of costing 90 cents, we cost $1.05 or something. But it's okay. And the nice thing about that is you use the inductor mostly just to cancel out capacitances. So now you make it real, and then you use the stacking tricks to get the real part to match fairly closely. So,
Can you do the matching?
the problem with the transmission line is that we're at about 900 megahertz, so the wavelength is like that, and your chip's like that. So getting a transmission line on chip is still not real practical. Typically, transmission lines start getting used at about 5 gigahertz and up. Yeah, that's where it even begins to be practical. And most of them are more at the 10 plus gigahertz range, at least on chip. Okay, now one of the things just to briefly touch on is how I set up the bias levels of the of this thing. And basically, I want everything referenced to the lower, essentially the VSS of the VCO. But I actually want to bias it above that. So I have a little bit of current into a diode, which sets up a higher one, and then I just have a resistive ladder. And the only trick here was to put in what amounts to a little current mirror right in the middle of the stack, so that when my supply voltage changed, I'd take it up on this place rather than across either of the individual amplifiers. And there's no particular obvious reason why this is the best way to do it, but just fiddling around with simulations, I found that I had the best sort of consistent performance if I let my supply variation appear here across between. Let me put it here. Let my supply variation appear between these nodes rather than across one of these individual drivers. Just kind of a heuristic thing. But this is kind of, I like this trick, that's why I put it in. Is that usually we think of mirrors as being sources or sinks, but this is actually essentially a floating current source right in the middle, because if you think about it, by pulling the current, so this is the idea, you have a ratioed mirror, you pull a little bit of current through the reference device, that forces the amount of current that both comes out of the source and the drain. As long as it stays in saturation, you've actually forced both currents, and that's the same as basically having a floating current source. It's a fun little trick, that's all. Okay, and just proving that it works, this is, I swept bias current to get P in, and then this is just a plot of that measured output power. You can see you can hit a pretty wide range, and the efficiency gets up to about 20%. That efficiency is actually the full radio, so that's the oscillator plus the dividers and things plus the output driver. So the output driver was more like 40 or 50% efficient, but then you have all like extra overheads. And that's kind of, if you get into the low power radio world, you find this a lot, that at the high performance end, typically people, when they want to make their radios, their transmitters low power, they just focus on the PA, because the PA is everything. If you make the PA 5% more efficient, your radio is almost 5% more efficient. But once you get to the lower power regime, you can always make PAs that are at least sort of 40 or 50% efficient. It's just not that hard. But then all the other stuff starts appearing as important, and it becomes a real challenge to get your oscillator to be really low power, and to get your PLL to be really low power, and any buffering you have down. So it's kind of a funny, different regime where the most important power things are not your actual PA, but other stuff. Okay, so now go on to the receiver. And we have lots of time, so ask more questions. This is the part that matters most for the project, so we can spend time on it. I'll talk about first the front end, the LNA mixer combination, and then the my more baseband IF stuff.
So if it's sleeping most of the time, sorry.
It's awful most of the time. When does it know to wake up to listen to the signal?
Because this little bit does not sleep. So you can actually implement a low frequency crystal oscillator for about half a microwatt. So this guy just runs all the time, and it has a counter sitting on it. I didn't implement that,
So how does it know when a signal is coming?
So it knows because signals are only sent once a second. So it counts first until a second hums, and it wakes up and listens. And if there's a signal there, the guy is talking to it also waited a second, and then while they're talking, they can resynchronize, and then they can shut down and wait a second and wake up again.
How long does it take for them to drift out of sync usually?
So crystal oscillators usually, their accuracy is kind of 50 parts per million or something.
I'm sorry, I don't know what that means.
So that means that that's a good way of thinking about that. My estimate of a second will be different from your estimate by a second by 305%. So a couple microseconds. So typically what you have to do in any system like this is you have to just assume that you're going to be, typically your receiver is on a little longer than you absolutely need to cover mismatch in timing. So you might turn on a little bit early, but you sort of assume you're going to turn on 5 milliseconds early. And if the other guy is in fact 5 milliseconds early, you're okay. And if he's 5 milliseconds late, then you're just on for 10 milliseconds doing nothing, and then he wakes up. But usually it's actually more like microseconds. So that's how you do it. So you're always running a clock, and then based on the clock you do various things, like you wake up and take a data point and fall asleep, or you wake up and talk to your neighbor and fall asleep. But you have to have the synchrony. There have been some attempts to make unsynchronized ones, and almost always they have to have some sort of sleep mode receiver that can sort of sniff power out of the air, and that turns out to be really hard.
When you're talking about talking to your neighbors, are you talking about a base station or just other smart dust modes?
I think the aggressive version is other smart dust nodes, and that's actually been implemented. Um, the first step is just to a base station, and then you know the base station has kind of infinite power and infinite time, and you just kind of let it synchronize you. But in a sort of a more ideal application, you're in an airplane, and you sort of dump them out the window, and they sort of fall down all over some piece of probably some foreign country, and then and then a week later the CIA sends a guy in there, and he comes in with his base station, quick records everything, he runs out again. And so for that whole week they're sitting there all talking to each other, sort of sharing data and figuring out what's important without any external interference. And then the spook shows up for 10 minutes and gets it all and runs. So that's the ideal funded version. All right, so let's go to the receiver. So just to remind us of frequencies, I implemented a low IF receiver, not a direct conversion, for some reasons I'll get into in a moment. And the frequencies were 900 megahertz and then an IF of about 1.8 megahertz. So a very low IF, but not true direct conversion. What you can see here over here is actually a conversion finally to baseband. So from an architecture point of view,
Al, what's the lowest frequency that makes it realistic to just do all the processing in DSP? I mean, that you don't have to go to baseband.
That's a good question. It really boils down mostly to your ADC. So there are two reasons to go all the way to baseband rather than just doing it at an IF. One is that you have to have a faster sampling rate on your ADC if you're at an IF. So for example, if I have a 2 megahertz IF, then my sample rate has to be 4 megahertz at least to meet basic requirements. Okay, so that's more expensive than an ADC running at 100 kilohertz. But the second problem is that it's harder to filter, so you're going to actually have to handle more interference, and so you'll also need more bits on your ADC. So it's a double whammy. Probably you have to go faster, and you also have to have 3 or 4 more bits of resolution to handle all those interferers you couldn't filter. So in this case, we went all the way to baseband. I didn't do that analysis in great depth, so it's possible that it would be more efficient to go straight to an ADC. But then you have to spend a lot of time designing a really good ADC, and that's not my forte. So, any other questions? There's actually another problem I'll get to in a minute that makes that even harder. Okay, so from a power point of view, basically we're stuck with either direct conversion or low IF, because anything else involves a high IF, and high IF means high frequency, which means power. So that's no good. I didn't do direct conversion for a couple reasons. Partly because I was very paranoid about them from having done them before. But they have a couple problems that are hard to beat. One of them is DC offset. Another is IP2, and then there's always flicker noise. And flicker noise becomes really hard at low powers, because typically the way you beat flicker noise is you make really big devices. And big devices means you burn more current or drive them harder. So a low IF avoids these because you go to a frequency that's away from those DCs, so you can filter them, but still low enough frequency that it's cheap to amplify. And so then you put in some more gain, you boost yourself by another 30 dB or so, and then when you do the final direct down conversion to baseband, you've got 30 dB more signal before you have noise. So it's a better solution. But there are a couple of problems with low IF. One is I have to generate an IF signal now for my oscillators. That's actually fairly easy. I can just divide down my LO, which I'm doing anyway, and just pick off that divided signal and use that as my IF. The other problem is that you have to supply image rejection. And my answer to that was to not supply image rejection. And I can justify that for essentially 2 reasons. There's 2 reasons you want image rejection. One of them is to not be interfered with by image signals. Okay, that's a really good reason. One way you can help reduce that problem is you make your IF programmable. So you can step your IF away from an image. So if you happen to, you might lose one packet of data because you wake up and there's something sitting in your image. But the next time you wake up, you move it, and you put your image somewhere else. And in the ISM bands, it's actually fairly sparse at the 900 band, so you can usually find an empty channel. The second problem, which is more severe or less avoidable, is the 3 dB noise figure hit. You just can't do anything about that. And the question is image rejection worth it from noise figure point of view? And basically what it boils down to in this case is to do image rejection would take more power from the LNA, or put another way, to do image rejection requires a certain amount of extra power. The place that power is going to come from is the LNA, because that's where all my received power is going, as I'll show. Well, when I take that power out of the LNA, its noise figure gets worse, and it actually gets worse by more than 3 dB. So it actually costs more to do image rejection than to just dump all my power into LNA and take the 3 dB hit. So in this implementation, no image rejection. And that'll show up.
You know what's signal and what's image.
Well,
Okay,
in some cases, you don't care. They're identical now, so you can use either one. The way you would know it in an actual implementation is you'd have some sort of some of your signal you receive, some of the bits in it would be telling you who's talking to you. And if it came out wrong, you'd be like, oh, that's not me. In fact, you'd probably get just complete gobbledygook. And
You were saying something about you can choose which you could shift your image, but you can just shift it 2 spots, right? I mean, you can have your LO either above RF or below RF.
For simple, that's the first thing you can do. But you can also, since you're deriving your IF from your LO by dividing it, you just divide by a different number, and your IF changes. And as long as you design your IF chain so it can handle different IFs, which is actually not that hard at a low IF, then you can also just change your IF, and so step not only which side your image is on, but what its offset is.
Would you also change your LO with respect to that?
Yes, you would. Yes. So you couldn't do it on the fly. You'd have to do it from different received packets. You'd have to change it. You have to just recenter yourself. Yeah.
Al?
Yeah.
When you say no image rejection, do you just mean no explicit image rejection filter, or you also don't do the quadrature thing?
Nothing.
Nothing.
So it really is an LNA and just a mixer, and nothing else. And I felt really not sure this was a good idea, and then I went to ISSCC, and other people were doing it too. I was like, okay, I'm justified. And they were doing it in medical implants, which sounds scary to me, because like one day someone turns on a radio in your image, and okay, so other things we just wanted to achieve. We were shooting for a sensitivity about minus 90 dBm. Why minus 90 dBm? Well, a little bit we did some intuitive calculations and said that for 10 meters we needed something like that. Mostly we did simulations and it was easy to hit 90, so that was our goal. To do that, though, that's not actually that easy. You need a lot of gain up front so that you can get above the noise floor of all your succeeding stages. And furthermore, if that's true, then your noise figure sets your LNA. So you just want to burn as much power as possible in your LNA to get its noise figure as good as possible, and then just kind of let the rest of the circuits, just barely eke by. The other thing that's noteworthy is since we're in the ISM band, the ISM band is mostly filled with relatively weak signals. It's a completely unlicensed band, so they're not really allowed to blast power there. So most of our interference is out of band, cell phones and things. On the other hand, we have no SAW filter up front, because those are expensive, and that'll be our whole buck by itself. So we're going to have to handle whatever wideband stuff is out there. So we need to be pretty linear, and I'll show you some neat tricks using passive mixers that allow you to be very linear. Okay, so here's my front end. Here's my LNA. That's an inverter with a resistor, correct? Only one neat little biasing trick. The VDD is not actually VDD. It's what they call self-biased. So you have a nice big AC coupling cap here that makes this look like a virtual ground, and then you dump a bias current into it. And what that means is that as long as you have enough headroom across this bias source here, you're really process insensitive. If your VT changes, so what? It just makes this little local VDD change. It turns out to actually be and the reason you care about this is this bias current is coming from your oscillator. So if this bias current changed dramatically based on random things in your LNA, that'd mean your frequency would shift because you'd be pulling your oscillator around and be a disaster. So you really want some good isolation there. That was the motivation. Now my mixer, yes, those are exactly 2 FETs, and they're switches. So basically, when the oscillator's cocked one way, this guy turns on, this guy turns off, and the output is connected to the input. Let's flip the other way, it's the other way. That's it. These are big capacitors, so the one nice trick, this is a really standard direct conversion low IF trick, is to filter as soon as possible. So that as soon as you come out of the mixer, you immediately eliminate blockers before they ever become voltage signals. So that you just flatten them right away, and that prevents you from having to be really linear after the mixer. The gain is relatively high, it's about 20 dB. That's voltage gain. The power gain of this is actually quite low because the impedance step up is gigantic. So
What's the cap at the output of the LNA?
these here,
Yeah.
this is parasitics. Yeah, this is not a real cap, but you have to include it when you do the math. So the gain here, it's worth noting, I made the resistor big. So it's not actually, I spent all this time matching the transmitter. The receiver is not that well matched. I just try to make this node look as high impedance as possible and get as much swing as possible. and the matching's not great, but there's no transmission lines or anything. It's just an antenna, so that actually doesn't work too badly.
So those are the figures of merit for the mixer and the LNA, or just for the LNA?
Combined.
So could you just explain that once more, biasing for the LN?
Okay, so the idea here is that if there's no signal, then if I get rid of the cap, if I just put current into this, I would basically have two VGSs, the VGSN and the VGSP, and this feedback guarantees that. And all the cap does is that, so at low frequencies, that's your voltage drop here. The cap just makes this look like a ground at high frequencies, so that I get the GM from this device and this device. That's all. So I use an inverter because, basically because I couldn't use inductors because they weren't any good in the process. So I need to have some sort of current source here anyway for a high impedance load from my common source. And that was going to be a PFET anyway. And then if I'm going to have a PFET, I may as well get a little bit of gain out of it by making an inverter. So this is not actually where's my arrow? This is not a 3-to-1 scaled inverter. It's actually a very different scale factor. There's an optimum mix of capacitance and GM that gives you the scaling that I basically did in Excel. Okay, so the noise figure is not great, but this includes that lack of image rejection. So it's really like a 6 dB noise figure for the structure. So it's actually not that hard to get a 6 dB noise figure. And the bias current through this is about 200 microamps. So not a whole lot. Now there's some cool things about passive mixers. This switching thing is called a passive mixer. It's passive because it has no inherent gain. It just basically is shorting different things together. One thing that's cool about it is if you ignore the LNA and look in from this side, you can see that this looks like what's called a switch cap resistor. Essentially, charge transfers from the capacitor. When this switch is closed, charge goes from this capacitor onto here, and then when it changes polarity, it comes back again. And so it actually, in composite, at low frequencies, looks like an RC and gives you an RC pole. So it gives you natural filtering. And then it does something really cool, which is that shows up on the input as well, because there keeps shorting the output of the input. And so you get what looks like a really high Q bandpass filter right there. And the cool thing about this is if you think about linearity, linearity is set by two things typically. It's set by the input linearity. So if I swing this input signal too much, I'll drive these things off. And by output linearity, which is if I swing this too much, I drive these into triode. What I've just done here is I've just suppressed my out-of-band signals by about 10 dB. And so I've made my output nonlinearity for out-of-band signals 10 dB better. And actually what it ends up doing is it means I can have a hell of a lot of gain and still have my linearity smashed out of band so that I compress the input and the output about the same time. So that's a really fun little trick out of an insanely simple circuit. All right, and I'm just going to talk a little bit now, my little chargers again, about what I was just, reiterate what I just said. So say we started out with a situation where the output voltage is fairly large, so all the charge is concentrated on one side of this differential pair of capacitors. Now when I do the switching, it does that. Charge gets transferred across. Also, my LNA has some inherent output resistance, some real part, and that can also, okay, so that gives me, back up, before I do the resistor thing. So if I just define mathematically what that does, from one cycle of LO to the next cycle, that's what the K is, the charge of the output will decrease by this ratio. Furthermore, some of the charge just gets dissipated out of the output, real part of the output impedance. So that gives me another little reduction term. However, I'm also driving the signal with a sinusoid input from my RF, which acts to restore the voltage difference across that output. So it gives me some input terms as well. Now, that's a really nasty equation, and I don't expect anybody to analyze that off the top of their head. But if you do, and you spend 15 minutes rearranging things, you discover that really the output voltage just looks like a single pole transfer function. So just to see that, basically, that's your single pole, right? There's your imaginary part, and this is your real part. This is all at the low frequencies. And there's a gain term that depends just on the frequency of your LO, and when you do all the math out, the parasitic capacitance. A bunch of things in here cancel in band. The one other thing to notice is, so this is just several different ways of modeling that. I did just plug this equation into MATLAB, and then I did two different, more elaborate simulations, in effect, of the same effect, and they match very well. So it's actually a pretty good approximation. Those simulations were transient simulations, in effect. The other thing that happens is that the input voltage here is continually, this node is either being shorted to one side or the other. So it essentially looks like an up-converted version of this output voltage. So you can approximate that as a sinusoidal version of it. And plus some extra terms where the current coming from the LNA is dropped across the parasitic resistance of your switches and a little bit of capacitance. And if you simulate that, the approximation is just basically taking, plugging this V out into here, or you do actual transient simulations. Again, you get pretty close matching, and again, predicting this cool bandpass effect. So that's a cool trick for making linear low-power front ends, is you actually basically have an effective filter immediately after your LNA, suppressing wideband signals.
What kind of selectivity do you achieve by that stuff?
Basically, the bandwidth is set predominantly by the ratio of your load capacitor to your parasitic capacitor. So that's, be more precise. Actually, it's right here. The bandwidth. This is the bandwidth. This is your offset frequency. So the bandwidth in terms of that offset from the LO is just proportional to this. So proportional to the period of your LO. That's what the T is. The ratio of the parasitic capacitor to the load capacitor, and then some extra R effects that usually don't matter very much. So it's basically just proportional to LO and to your capacitor ratio. So it means that it really is important to make the parasitic capacitance small. Turn off the wife, sorry. She'll be mad, it's okay. That's the answer.
And the rejection you achieve, you said it's 10 dB?
So then this bandwidth here, okay, so this bandwidth here is from this, the rejection down here is proportional, it comes from this term here, proportional to primarily to the channel resistance of your on switches. So basically, if you had none of these terms, then the V out just drops with frequency. But at some point, you hit a floor set by this kind of RF term. So in this case, it was about 10 dB. And it's actually, I've tried this in other processes, and that always seems to be a limit. It's really hard to get better than 10 or 12 dB.
So if linearity, say linearity was not a concern, why wouldn't, what's the advantage of an active mixer over a passive mixer?
Active mixers have gain. That's the basic benefit. So it's kind of a trade-off. When I was doing this design originally, I started out with an LNA and an active mixer because of that. And in the process I was in, the situation I was in, I found that it actually made more sense to sort of put all the power into the LNA and give it more gain, and then make the mixer passive, rather than doing sort of two stages. But that's not always true. It really depends on your situation. However, I do think the other thing is you can't just historically, active mixers have been popular for a very long time because you can't do passive mixers with BJTs. It's impossible. They have no triode state. They just go crappy when you try to do that. So I think part of the reason that active mixers are popular is they're just historically popular, and passive mixers have only been really practical since FETs got fast enough, which is like the last 3 to 5 years. So there's been less time for that development. Any more questions on this? No? Okay. So that was just we've already talked about this. So the wideband compression point of this thing was about -22 dBm. And as we'll see in later results, this is actually turns to be really conservative, because it turns out that models of passive mixers don't work very well from a linearity perspective. Just the way that FETs are usually modeled, it always assumes there's a drain and a source. And a completely passive switch, the drain and source are arbitrary. And in fact, the way the model handles it, it just takes whichever one is slightly larger and calls that the drain, and it calls the other one the source. So if you're swinging signals across it, once an LO cycle, it switches what's drain and what's source back and forth, and there's some discontinuity, and it makes things nonlinear. And that's all I know about that. But it turned out to be a very conservative simulation. Okay, so once I've gotten this far, here's my LNA and mixer combo. Now I need to gain it up some more. I've down to my IF. But before I can do that, I have a problem, which is that this is essentially still a direct conversion mixer. It's just that my signals aren't going all the way to DC. But there's nothing preventing other things from appearing at DC. And in particular, there's nothing preventing self-mixing of LO from appearing at DC. So what that's saying is I have an oscillator, it's running, it's generating a 900 megahertz signal. That signal's on an off-chip inductor, so it's radiating. Can't help it. That radiates over onto my antenna, comes in, gets gained up by the amplifier, and then mixed down, and it does the same frequency because it comes out at DC. So there's various isolation tricks you can play to make that less, but you can't get rid of it. It's always there. And now if you follow it up with 30 dB more gain, you're almost guaranteed to clip. You're going to saturate, because 30 dB of any sort of DC is huge. So to suppress that effect, there's a DC offset correction, and pretty much every direct conversion receiver out there has one of these. Sometimes they act like kind of like AC coupling. There's some sort of slow loop acting all the time. But usually you can get away with a calibration, because usually that self-mixing term doesn't change very fast. So you can just measure the DC, insert a correction that matches it, zero it out, and then start receiving data. Certainly most cell phones do that. So that's what I did here. This is just a little differential current DAC. You can just program in some offset to cancel out the DC offset coming out of the mixer. And then that's followed up by an amplifier. Again, it looks like CMOS inverters. My philosophy on this is that almost all CMOS is based on digital, and the basic digital block that they're trying to optimize is the inverter. So if you're trying to go sort of push on the power limits, the inverter is actually a pretty good way to go because it's been optimized. So here it is. All of these are running weak inversion, so they're all sub-threshold or sort of middle inversion. And the only real cool trick here is the way I do column mode. So I have a source up here, so this is essentially a diff pair we're looking at here. This is a diff pair too, but instead of having a pure current source here, this device is actually in triode, and its resistance is set by the column mode. So you can imagine if the column mode rises, that turns this device on more, which makes it draw more current and brings the column mode back. And so automatically the column mode of the output is fixed sort of in the middle of the supply range. It's not precise, but it's pretty good. So then we have a nice differential amplifier with a really high output impedance and column mode maintained. All right, now we get to by far the most complicated circuit you'll ever see. So now I want to downconvert again from IF to baseband. And this is actually, we'll touch on why just putting an ADC here is hard. The problem is, at this point, I've had essentially one pole worth of filtering at the output of the mixer. So I've suppressed harmonics of the IF by one pole's worth, so not very much. But rather than spending the power to amplify and filter some more, I'd like to just go down to baseband, because once I'm at baseband, filtering is much easier. I just make a low-pass filter at the band with my information and suppress everything. But we know mixers mix down things besides the wanted frequency. They mix down the third harmonic, the fifth harmonic. This is all differential, so that's true. All the odd harmonics come down. And in fact, any sort of sampling ADC will have the same problem. It'll mix down all the harmonics. So you would have to include a lot of anti-aliasing filter to go straight to an ADC, or I'll sample at a very high frequency. So how do I get around that here? Well, I start off with another passive mixer. So here's my IF amp I just showed you, and I'm just switching two sets of switches back and forth onto two caps. It's fully differential, and then amplifying that with another amplifier. That's pretty straightforward. Once again, we have that cool passive mixer bandpass effect, only now we're using it to suppress DC. So even with our DC offset DAC, we're going to still have some DC left over, and we're going to amplify it a whole lot. So it's nice to have some DC rejection, and this actually provides that. And it also gives us another pull from the capacitors in the output. Now I need quadrature because I'm actually trying to do full demodulation now. Quadrature is actually pretty easy. I just add a second combination. You think this is bad, just wait. A second set of capacitors, a second set of switches, and I turn them on at the 90-degree phase. Now I'm showing little pulses here. The idea is that each of these pulses is generated by dividing down my LO. So you divide your LO down a fair ways, down to sort of the right frequency, and then when you divide, you just notice, for example, basically you have, say, a modulo 8 counter. So it has 8 possible states. And for each one of those possible states, you turn on one of these switches. So it just changes configuration, turns on different sets of switches. And so some of those switches turn on at the beginning, some turn on a quarter of the way through, that's 90 degrees. Another one turns on halfway through, that's 180 degrees, and then the last one at 270. And now you've gotten quadrature for free. And variants of this is maybe the most common way of generating quadrature in an LO these days. Usually you have, instead of doing it IF, you have, if you're trying to do what I'm doing here with image rejection, you would have an 1800 megahertz oscillator, divide it by 2, and use the divide by 2 to have 0 and 90 degrees, right? So quarter of the way through, something changes and you divide by 2, and you grab that phase off. Do you want me to draw that? Okay. Can we go to the paper? So the basic idea is a divide by 2 would look like, that's right. You might do it like this. You have a D flip-flop. This is too small. I did learn from my feedback forms. So this is a T flip-flop overall. Every time you get a rising edge on the clock, it takes the input and feeds it to the output. Did I get that right? Yeah. And since that's inverted, it'll look like, say I started with a 0 on D, my clock comes in, that's my LO, right? This transitions to, the Q transitions, D is high, Q goes high, Q, D, clock. Now my Q is high, there's an inversion there, so that makes my D go low. The next time I see a rising edge, the Q follows the D, it goes down. That makes the D go high, and you can see it's dividing by 2, just every alternate cycle. Now, there's no phase there, but what if I put in parallel to this something the same, except I inverted the clock? So now it would be responding on the negative edges of the clock. So its waveform would look like that, switching on the negative edges. And if you compare, call that Q2, you compare this to this, you can see that they're 90 degrees phase split. And there's a natural, accurate 90 degrees phase split. This is probably the most common way now that phase splits are generated, because they're nice and accurate, and their sort of logic is so fast now that you can build these at really low power. Okay, back to the PowerPoint. Yeah, okay, so there we are. So now I've got quadrature. But I have a problem, which I still have all those third and fifth harmonics that I'm worried about. So now I'm going to use a really cool trick that was originally dreamed up by this guy Jeff Weldon on transmitters working at the BWRC, and now I'm applying it to receivers. And the basic idea is that when you shift the phase of a signal, of a sinusoidal signal, or any signal, if you shift the fundamental by a certain amount, its harmonics all shift by that amount times the harmonic number. So if you shift your wanted signal, or your fundamental, by 10 degrees, the third harmonic shifts by 30 degrees, the fifth harmonic shifts by 50 degrees, and so forth. Okay, the way we use that is we say, well, instead of using one signal, I'm going to use 3 signals, and I'm going to shift them by 45. So here's the fundamental. If I add up those 3 signals, they pretty much add in phase. They lose a little bit because they're not quite lined up, but it's pretty good. But the third harmonic, this 45-degree split becomes 135, and this negative 45 becomes negative 135. And if I just weight it right and sum them up, they cancel, and I get nothing. The same is true for the fifth. Basically, you can just see A and C is swapped here. And I get to the seventh, and I'm back to this situation. That's no good. So if I were just generating signals and adding them up, this would work. But it turns out this also works if I take a signal, multiply it by these 3 signals, and then add them up. The phase still cancels. I mean, there's no easy way to convince you of that except to try it out. It's actually a pretty straightforward thing. But in effect, what it does is it means that you've nulled out the third harmonic mixing term and the fifth harmonic mixing term, but you're still keeping the fundamental mixing term strong. Maybe let me just draw that, actually. Can I go back to the... So let me just draw those forms. So that's your basic LO. Then your other 2 LOs look like sort of like that, and sort of like that. So that's the equivalent of 45 degrees. Did I draw that wrong? And that's equivalent to 45 degrees. So shifted forward or back by 45. Now, I can do one thing I can do, if I just added these up, I would get a waveform that looked like right. You can sort of see this is already more sinusoidal looking than a square wave, right? Looks closer. So one thing I could say is, well, I could add them up and then I could use this as my mixing waveform, my LO. But then we lose all the benefits of being hard switched. I mean, we're no longer sort of a binary thing. We're some funky thing. However, what I can do instead is I can say, instead of saying, I've called this LO1, too small, LO1 plus LO2 plus LO3, and then multiplying that all by RF, or IF in this case. Instead, what I could say is multiply them first, LO1 plus IF, LO2 plus IF, LO3. Now, these 2 forms are mathematically identical, right? I just parsed. But implementation-wise, each of these LOs is now a square wave, so it's really easy to implement. And I just sum up afterwards, and I still get the same effect. There's no actual mathematical difference. So that's what I've done. And here's the nastiest thing you'll ever see, almost. So I've added all those extra phases, all those 45s and minus 45s, and all their complements. And so now I'm sampling onto eight capacitors, all these different signals, and then adding them up with the appropriate weights to get the cancellation. And yes, everyone who sees this, if I don't have the progression, people just laugh when they see this. All right, well, it works. So here's the simulation. This is using PAC, which you've all heard about now. I don't know what time it is. This is the filtering effect on the input. So looking into the mixer, you can see it has a nice sharp bandpass that likes the IF, actually likes the third harmonic of the IF as well. It suppresses DC. This is looking at the output. These are those different sidebands that you have to choose from in PAC. So that's the wanted. That's the third harmonic and the fifth harmonic. And you can see they're down by, we're down from the fundamental by almost 30 dB. And if it was pure square wave, they'd only be down by about 10. So we're getting about 20 dB help. And then there's even harmonics down here. So it works in simulation. I'll come back to measurements in a moment.
Why was this worth it instead of just doing so all we did was suppress the third and fifth harmonics from the mixer, right?
Right.
I mean, why would you go to baseband? Why can't we just do it in the digital circuitry?
Well, if you didn't do it, then those third and fifth harmonics would go to baseband with you, and you couldn't distinguish them. So any sort of interfere that was sitting on those frequencies would show up at baseband is indistinguishable from your wanted signal.
You can't pull them out using like a FFT or something?
Because let me draw that. So the idea is, it's on the spectrum, right? Here's your IF, your LO in this case. And you're looking for a signal that's sort of, there. You can't distinguish that from a signal there, because they both go there. So there's no way of telling them apart. And same for the fifth and so forth. The only you can do is you can add a filter. And so there is some filtering in here. There's a filter that looks sort of like that. So it actually, you're getting what I was saying, sort of one pole with a suppression on each of these effects. So basically, the signals that are here, before they get mixed, they've been suppressed by a filter. So we're suppressing this mixing term. The third LO and the fifth LO mixing terms. So this would not come, there's almost nothing here to come down. In fact, there's actually, because of the way the mixer works, there's actually two poles with the filtering. So it's one of the reasons I could just go for the third and the fifth and be okay, because the third and the fifth are so close that they won't be hurt very much by a real pole. But by the time you get to the seventh, that's essentially a factor of hopefully like 49 suppression. That's a lot of suppression, even without any funny mixer tricks. But the third harmonic, you're not getting more than maybe a factor of 10, and not even that, really. So that's why it's worth bothering with. All right, so then just finally there's a demodulator. This is a class of FSK demodulator. All it really does, let me go back to drawing. Thanks. Is if you have an FSK signal, let me just draw this out. And that means here's your LO, your low frequency LO. That means that's a 1, and that's a 0. Right? Either here or you're there, and you bounce back and forth. When you go to baseband, the way that comes out is in phase. So if you go to baseband, that's like having a positive frequency and a negative frequency, which translates to, in the I band, they both look like cosine of omega t, right? Plus or minus. That equals cosine of minus omega t. But for the Q band, you get cosine of omega t, which is equal to negative sine of negative omega t. So the phase flips. And so if you compare the phases, look at the I channel, you see some sort of sine wave that looks like that. In a one state, it lags, I think. So in the one state, the Q will look like that. In the 0 state, it's the opposite. So that's 1, 0. So I can demodulate this in a very straightforward way by just looking, whenever I go through 0 on the I, looking what state Q is in. If it's a 1, if it's high, that's a 1. If it's low, it's a 0. And so I could basically say, take that, put it in as the clock of a D flip-flop, and take this and make it the D part. What I do